Hello students, I'm back again with a new topic. In the last video, I have explained about the expression for longitudinal chromatic aberration when an object is at infinite distance. Today, I'm going to find out an expression for an object at finite distance. So the second case is for an object at finite distance. Now if you consider an object placed at an principal axis of a lens, so let's draw a figure for it. So the object at finite distance, let's say it is at here, a point object is at a finite distance. And this is a white light we are using. And for this white light we are getting images of different colors at different focal lengths. So I'm just drawing the extreme two ends of the focal lengths. So this is your IV and this is for IR, where IV stands for image for the violet color and this is the image for the red color. Now the distance from the object to the lens, let it be U, and the distance from the lens to the image be V. So as you are getting two extreme colors, that is for violet and red, so I will be having two image variables over here for violet as well as for red. So let's say this is my VV, this is the violet color of image distance of violet color, and let's say this is my VR for image distance for red color. Again, the focal length is given by 1 by f is equals to 1 by v minus 1 by u. This is a general formula, lens formula, you might be knowing this. Let's say this is my equation 1, where f is the focal length. Generally we say this is the mean focal length, and v is the image distance and u is the object distance. Now this u and v for a lens can be positive and negative. If it is towards your right side, then it is positive, and if it is towards your left side, it is negative. So in this case, my v will be positive, whereas my u will be negative. So now let consider FV and FR be the focal length for violet and red color, and VV and VR be the image distances for violet and red color. So we can express this equation 1 in terms of Vf as well as in terms of Vr. So let's do that. So 1 by Fv is equals to 1 by, now this V, as we are getting here two image distances, for violet is Vv and for red is Vr. So when you are considering for violet rays, so this will be, the focal length will be Fv and your this will be, V will be your Vv minus 1 by U. 1 by U won't change, U will be same. So let's say this is my equation 2. Again, when you are considering red light, so 1 by Fr is equals to 1 by Vr minus 1 by U. This is equation 3. Now subtracting, equation 3 from equation 2, we get 1 by Fv minus 1 by Fr is equals to 1 by Vv minus 1 by Vr, and these two terms will get cancelled out. So I'm just writing this one only directly. So this implies, when you're taking the LCM, so 1 by Vf minus 1 by, Fv, 1 by Fv minus 1 by Fr is equals to, just take the LCM on the right hand side, so we'll get here V into Vr, so over here Vr minus Vv. So this implies, we can take the LCM on the right hand side also, left hand side also. So Fv into Fr, here you will get a Fr minus Fv is equals to, on the right hand side as it is, that is Vr minus Vv by Vv into Vr. So you got a relation in this way. Now from this, now chromatic aberration, longitudinal chromatic aberration, we are finding out the longitudinal chromatic aberration. For this we need Vr minus Vv, that is the difference between the image distance. So Vr minus Vv, so we will get a relation in such a way so that we can calculate the longitudinal chromatic aberration for a finite distance. So this is equals to your Vv Vr divided by Fv Fr into Fr minus Fv. So let's say we can simplify this more also. Okay, if this is my two extreme colors, that is, let's say this is for Vv and Vr, this is a image distance for violet and image distance for red, and yellow is the intermediate of these two colors, so we can say this is Vy. So if we calculate Vy, we will write this as Vv plus Vr by 2, or else we can say that Vy square is equals to, we can say that Vv into Vr. Similarly, when you are considering focal length, let's say these are the two extreme focal lengths, that is Fv and this is Fr, and let's say this is a mean focal length, that is Fy. Generally we say F only, we can denote this as Fy. So this Fy is equals to your Fv plus Fr by 2. As this is a mean focal length, so mean always calculated in this way only. So Fy square can be written as Fv into Fr. So these values can be put over here and we can get a simplified relation. So Vr minus Vv is equals to, just put these two values over here. So here you will get as Vy square divided by Fy square into, this is your Fr minus Fv. So we can say this is the simplified relation for the chromatic aberration. Let's say this is my equation 4. Now, where you can note this as where Vy is the distance of yellow image and Fy is the focal length for yellow color. Again, in the previous video I have calculated the longitudinal chromatic aberration for an object at finite distance, and we got a relation as, that is Fr minus Fv is equals to omega into Fy, where omega is the dispersive power of the lens, and these terms are already explained over in the above expressions. And you can say that omega is nothing but mu v minus mu r divided by mu y minus 1. This is the expression for the dispersive power of the lens. So, putting this value in equation 4, we can get a relation as this. So, therefore, equation 4 becomes equation 4 becomes Vr minus Vv is equals to omega Vy square divided by Fy square, or Vr minus Vv is equals to omega by Fy square into Vy square. This can be the final relation for the longitudinal chromatic aberration when an object is at finite distance. Now we can write over here as this term is Vr minus Vb is nothing but the axial or longitudinal chromatic aberration. For an object at finite distance from the lens. Now let's do some problem related to this topic. Just write the question that a double convex lens has radii of curvature of 40 centimeter and 10 centimeter. Find the longitudinal chromatic aberration for an object at infinity. Suppose for an object at infinity. Given, and the question is mu phi is equals to 1.5230 and mu r is equals to 1.145. So here is a problem based on this topic, based on the two topics, that is the object when you are considering an object at finite distance as well as the object at infinite distance for a chromatic aberration, longitudinal chromatic aberrations. So here in the question it is written that a double convex lens has radii of curvature of 40 centimeter and 10 centimeter. Find the longitudinal chromatic aberration for an object at infinity. Given mu v equals to this much, this is the refractive index for violet rays and this is the refractive index for the red rays. Now let's solve this problem. Now we know that, see, as what is given in the question, just write down those values first. So it is given that R1, the radius of curvature, let's say R1 is equals to how much? Now 40 centimeter. R2 is equals to how much? Now minus 10 centimeter. Obviously for a double convex lens, R1 is positive and R2 is negative. And mu r is given as 1.5145 and mu v is given as 1.5230. So we need to find out what the longitudinal chromatic aberration. We need to find out longitudinal chromatic aberration. So this is the case when you are considering infinity. So we know that the longitudinal chromatic aberration when an object is at infinity is given by f r minus f v. It's given by f r minus f v. So let's calculate this term. You know this how to get this term. Now what we will do is we will separately calculate fr, then we'll calculate fv, then we'll subtract it and we will get the longitudinal chromatic aberration for an object at infinity. So how to calculate this fr and fv? Now we had a relation that is 1 by fr. There's a focal length, how the focal length is related to your refractive index. There was a relation that is 1 by f is equals to mu minus 1 into 1 by r1 minus 1 by r2. As you're considering two color, that is red and violet. So when you're considering two color, red and violet, what we can express this equation as 1 by f. Suppose for the red color you were considering, so 1 by fr is equals to mu r minus 1 into 1 by r1 minus 1 by r2. Now this equals to, you have these values and these values. You can put these values and you can calculate fr. So we'll put these values over here. 1.5145 minus 1 into 1 by r1 is 40 minus and this r2 is negative. That's why this becomes positive, so 1 by 10. If you subtract this, you will get a 0.5145 into, if you take the LCM of this is 40, so you will get here 1 plus 4, that is equals to 0.5145 into 5 by 40, that is equals to 0.5145 into 1 by 8. So this implies we can say 1 by FR is equals to 0.5145 divided by 8. This implies FR is equals to 8 by 0.5145. If you simplify this, you will get 15.549 centimeter. Similarly, if we go for the violet ray, we can calculate this value. So similarly, 1 by FV is equals to, here you will have mu V minus 1 into 1 by R1 minus 1 by R2. This is equals to mu V value is given as 1.5230 minus 1 into 1 by R1 is 1 by 40. This is becomes plus 1 by 10. So if you solve this one, 0.5230 into, if you solve this one, already we have solved, this is 1 by 8. So this equals to, when you are solving this, so FV, direct I am writing, this FV is equals to your, this will be your 8 by 0.5230, that is equals to 15.296 centimeter. So you got two values, that is FV and FR also. So now you are going to calculate the longitudinal chromatic aberration. Thus, the longitudinal chromatic aberration is given by, that is FR minus FV. We had a relation with this. There is a difference between the two focal lengths, extreme focal lengths. So this gives you how much? Now we got red color. Here we got the red color as 15.549, and for violet color you got 15.296. Just put these values. So we'll get here 15.549 minus 15.296. You subtract this, you will get here 0.253 centimeter. So this is how you calculated the longitudinal chromatic aberration when an object was at infinity. This is a problem we calculated. Now next, the second question we are going to do. A lens made of crown glass has focal length 40 centimeter. Calculate the longitudinal chromatic aberration if mu V is given 1.5249 and mu R is given 1.5164. So how to calculate this problem? How to do this problem? Let's see. Now a lens is there, it's made up of a crown glass, has focal length 40 centimeter. Now when in a question it is given that it's a focal length is given, that means that this is a focal length for a main color. That is, it is a focal length for Fy. Calculate the longitudinal chromatic aberration if mu v is given and mu r is given. So just write the values given first. So mu v is 1.5249, mu r is equals to 1.5164, and the focal length, this is the for yellow color, that is the mean focal length, which is equals to 40 centimeter. This is the mean focal length. Now how to calculate? You have only these values, no other values are given. So how can you calculate longitudinal chromatic aberrations? Now you had a relation, that is, in your topic you had a relation, that is omega is equals to mu v minus mu r divided by mu y minus 1. Why I am considering this is because for the longitudinal chromatic aberration we had a relation, that is fr minus fv is equals to omega into fy. So here we need to calculate this. So with us we have only this value, we don't have this value, so we have to calculate this value. For this value we have some data, so we can calculate omega, we can put this value here, and we have this value. So product of these two gives you the longitudinal chromatic aberration. So we are going to do the same thing. So let's start calculating omega. Now mu v, how to calculate mu y? Mu y is not given. You have mu v, mu r. Mu y is not given. So how will you calculate this mu y? You know mu y, this is nothing the mean refractive index, which is given by mu v plus mu r divided by 2. These are two extreme points. See here, this is mu v suppose, this is point is mu r suppose, so mu y is in between these two, in intermediate, it is in the mean position of these two points. So that's why you can say that mu y equals to mu v plus mu r divided by 2. So from this you can calculate mu y. So you will get here mu v value is 1.5249 plus mu r value is 1.5164 divided by 2, which gives you 1.5206. So this is a refractive index for the yellow rays. So now longitudinal, now let's calculate the longitudinal chromatic aberration. So which is given as fr minus fv is equals to omega fy, that is equals to omega value you have got. Okay, you have it. You just put the values of omega, that is mu v is equals to, say, omega is equals to mu v minus, here this is a relation, mu v minus mu r divided by mu y minus 1. Just put these all values, you have it, and calculate. So in place of omega you are going to write these values, putting these values, 1.5249 minus 1.5164 divided by 1.5206 minus 1. This is for yellow, refractive index for yellow. You have calculated into fy is given, that is 40 centimeter. So when you are calculating this, you will get fr minus fv is equals to 0.0656 centimeter. So this is how we calculated the longitudinal chromatic aberration for this problem. Thank you.